According to a recent survey, 83% of students say that they do not get enough sleep. Assume the survey meets the conditions of a binomial experiment. Round your answers to 3 decimal places. In this situation, we can already assume, because we've been told, that we can answer with binomial probabilities. So, when answering with binomials, we just need to make sure we come up with the important inputs, which the 2 most important are n and p. N is the number of trials in the experiment, p is the probability of success. So we have a random survey of 20 students, and we want to see the probability, the probability of success is 0.83 because 0.83 say they do not get enough sleep. And what we want to observe is that exactly 17 of them, so x is equal to 17. So when we see this wording of exactly a certain number of items out of our sample, we will solve using Binompdf. The inputs to Binompdf are n, p, and x. So n is 20, p is 0.83, and x is 17. So using the calculator to come up with our solution, second and vars takes us into the distributions menu. And if you scroll down a bit, you'll eventually run into the binomial functions. We have Binompdf and Binomcdf. So Binompdf is what we want in this case. 20 is the number of trials, 0.83. We separate this information with commas, of course, and then 17. So 0.2358. And that's the probability that 17 out of 20 do not get enough sleep. In a random survey of 20 students, find the probability that more than 17 of them will say that they do not get enough sleep. Now, in order to answer this, the language has changed a bit. We're looking for the probability that more than 17 of them do not get enough sleep. So in this case, we could technically solve this using Binompdf. But what we would have to do is evaluate Binompdf with the first 2 inputs, which are always n and p. We would have to do it once with 18, because 18 is more than 17. But so is 19, so we would have to run it a second time. And so is 20. So we'd have to run it a third time and add those 3 values together. So we could come up with it using Binompdf, but sometimes it's a little bit easier to use Binomcdf instead, because a cumulative distribution function already has items added up together for you. Because in effect, what we're trying to do when we have binomial probabilities that are complex like this, we have 20 trials, probability of success is 0.83, and just go up to 20 and leave it. This is what our binomial distribution looks like. So these are the probabilities for each number of trials. Notice they're all very small. In fact, Binompdf rounds to 4 decimal places of 0 in all of those cases. It isn't until you get to 9 and 10 trials where Binompdf has some probability. But then you have your probabilities increase greatly off to the side here, and then they kind of dip down again. Effectively, what we're trying to do is we're trying to find the probability of 18, 19, and 20, because those are all the probabilities that are greater than 17. Now here, the program reports it to us right as 0.3146. But unfortunately, we don't have a binomial program in the calculator that will allow us to put a lower bound and an upper bound in. What we have is two functions, Binompdf and Binomcdf. So you have two options here. You can either use Binompdf 3 separate times and add the results together. That wouldn't be too bad in this case, but if you have more than 3, that's a lot of typing. You can also use Binomcdf. What Binomcdf does is, you can kind of see it from here. It starts with the probability of one event, adds the next probability, and gets a total. Adds the next probability, so 0.0007 plus 0.0026, 0.0033. And it keeps doing a running total of probabilities, so it's already adding things together. Now, it's starting from 0 and going up to a certain number of outcomes. So it's not helpful directly, but it is helpful indirectly. Because if I get the Binomcdf of 17 trials, that would tell me the sum of all of these white histogram bars. And that's complementary to the sum of these 3 blue ones. So what I can do to solve this problem is use Binomcdf, and it takes the same inputs. It's still n, p, and x. The value that I want to use for x is the cutoff for the complement of what I'm looking for. So the cutoff for the complement, since I want more than 17. So I want to add up all of the binomial histogram bars. We can think of them like that. But all the binomial probabilities up to 17. And then if I take the complement of that, that's going to give me instead the sum going from 18 to the maximum. And that's what I want, because if I want more than 17, I want 18 to 20. Okay, so let's try this out. All right, so 1 minus distributions. I come down to Binomcdf. There are 20 trials. Probability of success is 0.83. And I want to add up everything up to 17, up to and including 17, and then subtract that sum from 1, because that's going to give me what's left over from 18 to 20. So in this case, 0.3146. And that matches what we had come up with right here.